Yeah, it's a great privilege to talk to you here, and I should say, as one of the locals, welcome to Harvard. I hope you all have a great workshop while you're here. It's nice to see some friends and collaborators who I haven't interacted very much of late. Well, the fonts don't look so good, but hopefully the talk will be okay nonetheless. I'm going to try, because Dan has just given a very nice introduction to some of the classical theory, at least, which applies for the most part. I'm going to try and just kind of bring you up to where we are experimentally and what's going on. And cold antihydrogen, of course, we're meaning temperatures. I've shown this scale for a long time, but we're talking about now that temperatures which are not at 4 Kelvin, which is where we've typically worked, we actually have some of our plasmas down at 1 Kelvin, we think, though we're not exactly sure what the temperature is. More about that in a moment. And we've been going at this for a long time, and Steve Ralston, in fact, was here in the early days of the antihydrogen stuff. I think when we were all thinking about where we would go, we never really thought that this antihydrogen business would become such an enterprise, okay? But now there's a lot of people trying to produce cold antihydrogen and trap it. There's also alternative approaches. Let me just say what teams are going on. The particle physicists at CERN were nice enough to build us a dedicated storage ring, which doesn't happen so often, so we're very fortunate and grateful to them for that. We're hoping that they're also going to now upgrade that storage ring. We're working hard to see if we can get the antiproton flux up by a factor of 100 or so. There's our collaboration called A-Trap. Oh, I should have written alpha here. I just typed it in too quickly. It was Athena and it's become alpha. I apologize. And there's Exacxa, and then there's a new collaboration called Aegis. Now, I'm going to mostly illustrate using the A-Trap experiment, but for all practical purposes, the alpha experiment is doing much the same as we are. There's important technical differences and approach differences between the two experiments, but there's a lot of similarities as well. That is to say, we're both using a recombination of the same type for the most part, though we're also trying to do a laser-controlled method. And we're trying to put a magnetic trap around the antihydrogen. Exacxa is taking a different approach. They're using something called a cusp trap, which is really a spherical quadrupole trap, spherical quadrupole field, and it'll trap charged particles and it will trap neutral particles in, and it doesn't have some of the symmetry problems that Yaffe traps might have. Aegis is actually also half of Athena, so Athena has morphed into alpha and Aegis. These folks want to do antihydrogen interferometry, which I think is a little ambitious given that we don't have any atoms cold enough to do any interferometry at all, but they're hoping to do that on a fairly short time scale. Okay, so that's the basic idea. I'm going to skip through the motivations for this for the most part. Let me just say the following. Our basic goal is to make a precise comparison of antihydrogen and hydrogen structure using laser spectroscopy. We hope to do that at a very high level of accuracy. The hydrogen natural line width is in here. You know, we won't be limited by that. We'll be limited by our trap. But the point will be, if we compare a Rydberg and an anti-Rydberg, for example, it will depend on all these charge and mass ratios of particles and antiparticles, which by the CPT theorem should be the same. Okay, and so if the Rydbergs are different, we'll have some sensitivity to a lot of different quantities. That's the basic idea. We'd like to use laser spectroscopy, but I mean, we could use microwave spectroscopy as well. This is the famous Hench plot where, you know, there's all these measurements which get more and more accurate as time goes on. He stops his plot at 2000 because there's been no progress since. So there's actually a flat line here. But okay, but it is a remarkable progression of accuracy nonetheless. Okay, now let me switch now to the A-Trap experiment. We need a collaboration to do these sorts of things. These are the people that are currently on board. Andrew Speck, who will speak next for just a few minutes, is part of this collaboration. He was a graduate student in our group, but as I said, he's at the Roland Institute right now. Okay. Here's what our apparatus looks like, and there's a 100-second clock, roughly, 110, 90, depends on how the antiproton decelerator is running. But what happens is we load antiprotons, which come from CERN this way, and positrons from a radioactive source, which accumulate in our trap, and then they go around this absolutely awful beamline. Who would design a beamline that looks like a triangle, right? Okay, the reason for that is we have a big fringing field, okay, and we have to follow the field lines into this solenoid. So we have to come over here and then sneak onto an edge of a field line and come back in. Now, if you compare the apparatus to the alpha experiment, our neighbors, they also have a similar accumulator. In fact, they had one like this before we did. And they get antiprotons. They just do everything in a horizontal axis, okay? And we prefer, for technical reasons, to do the vertical axis. In addition, there's not enough room at CERN to have more experiments, all of which have a horizontal axis. So twice per AD cycle, the AD cycle is once every 100 seconds we get antiprotons come in. Twice per AD cycle, we transfer positrons in. So we can then accumulate the antiprotons and positrons, and a typical measurement that we do, and we do it about once per hour, okay, so the data rate is excruciatingly slow. We get of order, you know, we can use 1 million antiprotons, let's say, and maybe 60, 70 million positrons, and that's what we have available to put together to make antihydrogen, okay? Here's a picture of the inner guts of our apparatus. There's a really big solenoid, which I could fit inside if I were a little less portly. I'm biking again, so there's hope, but not yet. Okay, and the apparatus, here's a real picture of it. Here's a CAD drawing. It's in a superconducting solenoid. The windings of the solenoid are about 1 meter long, a little more. Okay, and then inside of here, there's a helium dewar, which keeps things cold, and there's trap electrodes the whole length of this thing. Okay, and so we capture antiprotons. They come in from the bottom, and the positrons come in from the top, as you saw on the last slide. And here's a picture of what it looks like when it's all together. Now here's the apparatus that has electrons in it. I don't know what happened to Steve's fonts here. So is it really in our paper with electrons?
Where do you think I got that figure from?
Oh, I think what you did is I think you got the electronic copy and someone played font games with you. But okay, it's electrons, whatever it said. This is a cross-sectional view. There's lots of electrodes. The antiprotons get captured in this region. The positrons get captured in this region. Then we transfer the antiprotons over to the central region and we do experiments. There's a Yaffe trap that's around, a quadrupole Yaffe trap in our case. The alpha experiment uses a higher order trap, an octupole. That's just the number of these current bars. These are superconducting current bars to get lots of current in to get the deepest possible trap. Even if you work really hard to do it, you only get a fraction of a Kelvin deep trap for an antihydrogen atom. And that's why cold is very much better, because even if you have a 4 Kelvin distribution, all of the antihydrogen atoms, all of the atoms will have too much energy almost to be trapped. Okay, that's the apparatus. Okay, the basic methods for capturing the antiprotons we developed many years ago. We slow the antiprotons in matter, we capture them in flight, we do electron cooling, and we get them at 5 times 10 to the minus 17 torr. These methods are now common to all of the apparatus. Here's some movies which just show the antiprotons coming in. When they're inside, you slam the door shut, and then you oscillate the antiprotons back and forth. This is the same basic method that all the experiments use. The one variation is there's an RFQ decelerator used by the Exacxa collaboration, which replaces a thin metal window. At least it makes the metal window thinner, and they slow it down in a proper decelerator machine, and they get about a factor of 8 more antiprotons than we do in the trap per injection. Okay, so that's a substantial amount. There's a proposal now at CERN to build a small storage ring, which would fit sort of in the front of this room almost. Okay, and that storage ring, if it didn't cost so much money, would give us 100 times more antiprotons. And we're getting things funded right now in this climate is a little tricky, but we'll see. Okay, now once we have antiprotons in, or even before, we can put electrons in. We do electron cooling because the antiprotons hit the electrons radiate synchrotron radiation, and so on. That's sort of a familiar story. We then arrange the trap potential so that we let the electrons escape, and the antiprotons are left behind. Okay, now the temperature of the antiprotons now is a little bit of a tricky thing because they're not being kept cold anymore. And so sometimes we'll put a few electrons back in there because the electrons will radiate synchrotron radiation and keep the antiprotons cold. Okay, there are two methods right now to produce and slow antihydrogen in a nested pinning trap during positron cooling of antiprotons. Okay, and there's a laser-controlled resonance charge exchange. I'll just remind you of these. We use what's called the nested pinning trap because the positrons have an opposite sign of charge of the antiprotons, and so we have to put them in a trap which they both see a potential hill, and they tend to see a different concavity because of their opposite sign of charge for a potential well. There's also the three-body rate that Dan was just talking about. We noticed that this was going to have a very high rate many years ago, but we were very concerned about the magnetic field and its effect. And in fact, the Glinsky-O'Neill paper that he talked about was a very important development because we went to them and said, folks, this can't be exactly right because there's a strong magnetic field, and that's not included in these traditional papers that Steve was talking about. Unfortunately, Steve still doesn't include much of a magnetic field, though I'm hoping he changes that someday. Here's the basic way that we make the antihydrogen, or the circumstances that we arrange. The antiprotons go back and forth through the positron cloud in this nested well, one well nested inside of the other, but they're inverted. And when the antiprotons are going really slow, that's when the antihydrogen is formed by the three-body recombination process, mostly by replacement collisions, and so as you heard in the last talk. Okay, the other method is more complicated, and it's one that we're focusing on this year again. Okay, we demonstrated it a few years ago, but haven't really used it because we produce so few atoms. The basic idea is to take cesium atoms, excite them with a couple of lasers so they have a really big orbit. Then they're likely to interact with trapped positrons that we have ready for them. The trapped positrons form positronium because the electron jumps off the cesium atom. The positronium in this excited state goes all directions. We have some trapped antiprotons nearby, and the positron can jump off the positronium atom and onto the antiproton. We form excited antihydrogen, which then we ionize in a well. So the solid angle hit is pretty large in this experiment, and we didn't see many particles. Compared to when we demonstrated this a few years ago, we now have, instead of maybe 100,000 or 200,000 positrons for a typical experiment, we have 80 million, okay, and we have about 1 million antiprotons instead of maybe 50,000. Okay, so we've greatly scaled up the size of the plasma. That makes the interaction probability much higher. It also gives us some hope that there's enough of a plasma that there can be collisions to de-excite the particles inside of that plasma. And that's what we're working on right now. Now, we wrote a couple of papers. This is the second one. Some people had said in PRL, so we thought it might be true, that if you used a quadrupole trap like this, you couldn't possibly form antihydrogen inside. And we felt bad about that because we were building this nice quadrupole trap, so we decided to try it anyway. And in fact, we did demonstrate that you can produce antihydrogen inside of this despite the fields that are put on. Okay, the fear was that these fields would make the positron and the antiproton plasmas unstable, and so you wouldn't be able to hold them long enough to form the antihydrogen. And fortunately, that turned out not to be true. Now, this is our latest thing, which, Dan, this is what I was talking about beforehand. We've been focusing a lot on trying to get really cold plasmas because we've also been looking to try and trap antihydrogen atoms in this trap. We haven't seen any. There's two possible reasons. They're not de-excited enough, okay, or they're not cold enough. I think they're likely not cold enough, so rather than just try it endlessly, we focused on getting colder plasmas, okay? Now this is an electron plasma. We can do it just as well with positrons, of course. Electrons were just cheaper for the demonstration. Here's the nice thing. You can see that we changed the temperature of our electrodes, that's shown in black, these are real temperature measurements, by about 3 degrees. And the temperature of our electron plasma tracked very well this 3 degrees. Now, the method that we used was a method that, at least the basic element of it, was introduced by Dan Dubin, who you just heard talk. There's some plasma resonances inside of a cloud of electron, and they're temperature dependent. Okay, now he calculated this in a nice ideal case for a spheroidal plasma. We don't always have spheroidal plasma, so we have to sort of recalculate it numerically to account for finite boundary conditions. But the ideas are basically the same. Now in this method, you don't really know what the zero of the temperature is. So we maybe could have 10-degree plasma, which is going up by 3 degrees, but it seems highly unlikely that that temperature would just change exactly, you know, by 3 degrees if we were at a different baseline. But okay, this is what we were able to measure. If indeed there's two temperatures in the plasma, because the radial degrees of freedom around the magnetic field with respect to the magnetic field axis, if those cool by synchrotron radiation and the axial degrees of freedom do not, as some people claim, then I'm not sure exactly what temperature we're measuring. We're probably measuring the axial temperature. I've been talking to Dan about redoing his calculations so that he can put two temperatures in there, and he thinks that that can be done, and we can see what happens. Now, why is, 4 Kelvin down to 1 Kelvin, big deal? It's only a factor of 4. Well, it actually is a big deal because it happens in the exponent. Okay, in a Boltzmann distribution. So that means that we get a large, many more antiprotons that are cold. Okay, I just mentioned the question here, but the one difference between the alpha experiment and ours is the number of current bars. Okay, I won't go into that right now. We're building, here's our first generation Yaffe Trap. It's a metal thing, you know, which is held together very strongly in a traditional way, as Yaffe traps have often been made when they're superconducting. And I mention that because, you know, that's this thing here. We're building a new one. This one, the manufacturer says you can turn off in 10 minutes. And if you go faster than that, you void the warranty. Okay, we went first to doing it in 1 minute, and it didn't break. So now what we do is we actually quench it by putting a heat pulse in deliberately. And the idea is to dump the trap very rapidly so that if there's a small number of antihydrogen atoms, we can see them in between the background counts, you know, from annihilation signals. That's not very elegant, okay? And it takes you a while till you get the nerve to take such an expensive thing and quench it, you know, too many times in a night. And so we're doing something which is maybe not safer. We now have a glued together system which has almost no inductance, so we can ramp it out, we think, in a millisecond or so. And this Yaffe trap is all made on G10, and it's going to be glued together. And there's wires that are actually potted into the sides of tubes. And in fact, while Tom was talking, I got an update. This is the latest picture of the latest layer added to our thing. We have octupole layers, and our first of our quadrupole layers is now wound on this system. Okay, it has yet to be tested. Now, one scary thing is the company that contracted to do this tried to glue pieces together, because you have all these laser access ports and stuff like this, and of course there's 1,000 amps going through here, so there's got to be a little mechanical rigidity. It's all in a up to a 3 Tesla field. They couldn't glue things together. Their test pieces kept breaking. So they said they couldn't make it, whereupon I have a graduate student who's very good, built all these test jigs, and he demonstrated that we could glue it together properly, so we'll keep the fingers crossed. As far as I know, it's the first strong Yaffe trap that's been built that way. We're searching for antihydrogen ions. I'm not going to talk about that so much. There the idea is that we could, here's just the one antiproton signal so we can do it. Well, okay, and it's moving along. But the basic, we did this years ago with antiprotons. Here the idea is to look for the anti-H minus or the anti-H2 plus ions, okay, because we can do that with one particle sensitivity. That's just beginning. It's not a real high priority for us, and we're going to see where that goes. Okay, now we're trying now to do this experiment, as I said, with bigger plasmas and better sources. Okay. Now the summary here is that really much has been accomplished, but much remains in the antihydrogen business. I've been saying that for a long time. I would say we keep making steady progress. Our plasmas are much better characterized right now. Okay, we understand much better what we're putting together. We can measure the temperatures much better. We have hugely more particles and so that we can do. A side experiment is we're trying to measure the antiproton magnetic moment. There we're building on the success we had here at Harvard in measuring the electron magnetic moment to 3 parts in 10 to the 13 and getting the fine structure constant measured very accurately. There's a double trap over at Harvard that has 1 proton in it right now, and I don't have time to talk about it, but we hope that we can eventually probably improve on Dan Kleppner's measurement of the proton magnetic moment by an order of magnitude or so, but that's not really the point. The real point is we can probably improve on measuring the antiproton magnetic moment by a factor of 1,000,000 or more. The trick is we want to observe a single proton spin flip, okay, in a non-destructive way. Now we observe single electron spin flips, but a nuclear magneton is 2,000 times smaller than a Bohr magneton, and that's the challenge of the measurements. Here's a signal from 1 proton. The green line shows the sensitivity that we think we have. Statistically, we have it, but this doesn't tell the whole story. This is these are line width measurements, and what we get is a slow drift, a wander around of this frequency, which is bigger than this by about a factor of 2. And so we're close, but it's not working yet. Okay, there's my summary, and I'm going to quit here and ask Andrew to come up and just finish off for a few moments. Okay, the antiproton and hydrogen update, I went through all of these points. I won't say them again. Andrew is going to talk about the possible use of optical half-cycle pulses to de-excite Rydberg antihydrogen, which is an effort taking place in his lab.